So in 12.1, we're going to talk about a sequence of a function we're going to talk about a sequence. And a definition is that a sequence is a function whose domain is the set of positive integers. So basically, you've already been working with things like this before, but I just want to kind of show you what it means graphically. So if we look at this graph that I have right here, okay, if we look at this graph, that is the function f of x equals 1 over x, where x is greater than 0, okay? So if we look at this, we notice that I plotted some points and then I connected the dots and I have my function. So that's what it would look like, okay? And this is totally fine. You guys know how to plug it in. You would do f of 1, you'd plug it in and you'd get 1. You'd do f of 2, you'd plug it in, you'd get 1/2. You do f of 3, you plug it in, you get 1/3, so on and so on, and we could go forever. But you could also plug in f of 0.5, right? And if you plug 0.5 in there, you'd get 2. If you plugged f of 2.4, you would get 1 over 2.4, right? So we could do this all day. Now the thing is the domain of this function is x is greater than 0, and x could be any real number. Now the difference, what we're going to be doing in 12.1 is we're not going to connect the dots. What we're going to be dealing with is just those coordinates. So I do the same thing. I say f of n when n is 1, f of n when n is 2, f of n when n is 3, and we get the same exact values, 1, 1/2, 1/3. The difference is we cannot pick f of 1.7. We can't do that because the domain of a sequence is the set of positive integers, okay? So that's what we really have to notice. The difference is in here, I could pick all these values here, 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 here. I could pick all these points, all these little values right here. But here, this is where it has to go. It has to go here. It has to go here. I cannot pick 3.7 as a value to plug into my sequence. So that's the big thing about sequences. They're still functions. They're still behave just like normally they're written either as f of n or a lot of times they'll be written like this. And I've even seen it just sometimes written like a sub n. Okay, but in general, you don't connect the dots. You just have those terms, those values. Okay, so to me, I always just thought of a sequence as a list of numbers or a pattern that is generated from some functional value or something like that. Okay, so just to do some work with sequences, what we can do is we can write out the terms of the sequence, and normally they ask you to write out like the first 5 terms. So this will just be good practice for us to plug values in and see what happens. So when they say a sub 1, they literally mean you're going to take 1 and plug it in for n. So that means it has to go there as well. So if we say that a sub n is equal to n squared plus 1, we're simply going to do 1 squared plus 1, which is 2. If we say a sub 2, then a sub 2 would be 2 squared plus 1, which is 5. This would be 3 squared plus 1, which is 10. This would be 4 squared plus 1, which is 17. And this would be 5 squared plus 1, which is 26. So we have our pattern. Our pattern is 2, 5, 10, 17, 26, right? And it could go on and on like that. Okay, so we've generated the pattern. Okay, now let's pause the video and have you guys do this one real quick. A sub n is equal to 2n plus 1 over 2n. So go ahead and take a minute to try to get those first 5 terms. Okay, so hopefully you guys literally just plugged in 1 and you would get 2 times 1 plus 1 over 2 times 1. And that would be what? 2 plus 1, which is 3 over 2. So we get 3/2 or 1.5. Here we're going to plug in 2, so we get 4 plus 1. So this would be 4 plus 1 over 4, which is 5 over 4. Here we're going to get, I'm assuming, 7 over 6. This one we're going to get, 9 over 8. And let me see, make sure I did that right, 9 over 8. And then the next one we're going to do, we're going to plug in 5, and we're going to get 11 over 10. So here's our pattern. 3/2, oops, let me write it over here. 3/2, 5/4, 7/6, 9/8, 11/10, and then we could just keep going. So this is the first 5 terms, but we could ask for the first 15 terms or 20 terms or whatever, right? So this is how, when they ask you to generate the first few terms of a sequence, all you do is you plug in a sub 1, a sub 2, a sub 3, a sub 4, so on and so on and so on, okay? Not so bad. Okay, so take a minute to write all these down. This says determine a sequence from a pattern. So now, instead of giving us, and by the way, just to note, this is oftentimes referred to as the general term. Oops. Also called the nth term as well, because if you have this formula, that means you can find any term that somebody asks us, okay? So I've seen it called the general term. It's loosely called the nth term. So this just means that if I give you this, you kind of have everything you need. So the harder part is if they just give you the pattern and then they want you to come up with that formula, okay? So we have e, comma, e squared over 2, comma, e cubed over 3, comma, e to the 4th over 4, so on and so on and so on. So we need to come up with some a sub n. A sub n is equal to what? What would be a pattern? Well, just so you guys know, the way, as they get more complicated, this one isn't so bad. I normally always try to look at the numerator and the denominator as 2 separate problems. So what would generate an e to the 1st, an e squared, an e cubed, and e to the 4th? Remember, this is a sub 1, a sub 2, a sub 3, a sub 4. So I'm trying to match the subscript right here with the power maybe, okay? So let's see what that gives me. That would be e to the n. If I plugged in 1, I get e to the 1. If I plugged in 2, I get e squared. If I plugged in 3, so this would generate the numerator. Now the denominator is 1, 2, 3, 4, so that's just n. So I get e to the n over n, nice and clean. Okay, now let's look at this one. Let's see here, 1, 3, 5, 7, 9, so on and so on. This is the odd numbers, right? And you guys should know that the way to generate an odd number is 2n plus 1 or 2n minus 1. Which way is it though? Well, if I did the plus 1 and I plugged 1 in, I would start at 3. Because this one starts at 1, I can't use this guy, I have to use him. So I have a sub n is equal to 2n minus 1. And what I normally do is I then try to double check. So in my mind, I take and I plug in 1. So I'd get 2 times 1, which is 2, minus 1 is 1. Plug in 2. 2 times 2, which is 4, minus 1 is 3. 2 times 3 is 6, minus 1 is 5. So I would definitely be able to generate this pattern with this general term or with this nth term. So now let's look at this one, a sub n. Okay, this next one says a sub n equals, now again, the numerator is nice, it's just 1, right? But the denominator looks like it's what, 3 squared would be 9, 9 squared would be 81, so that doesn't work. Or isn't it just powers of 3? So 3 to the 1st, 3 to the 2nd, 3 to the 3rd, 3 to the 4th. So if I just wrote 3n, then I'd plug a 1 in there and I'd get 1/3, so I would start here. But I need to start at 1. So what could I do that when I plug a 1 in, I would get a 0 power? I subtract 1 from the power, just like that. So this becomes 1 over 3 to the n minus 1, okay? And now if I try to generate some terms, let's plug 1 in. I get 1 over 3 to the 0, which is 1. Now I plug 2 in. 1 over 3 to the 2 minus 1 would be 1 over 3. Boom, I get 1/3, and so on and so on, and this will work. This last one. Now this one, notice it goes plus, minus, plus, minus, plus. So that's called an alternating series. So you got to be a little bit more careful of those. It's not end of the world stuff or anything like that, but we do have to be a little bit more careful. So the numerator, once again, is nice. We're going to say a sub n is equal to 1. The problem is the 1 becomes positive, then it becomes negative, then it becomes positive, and then it becomes negative. So what I'm actually going to do is I'm going to call it -1, okay? Because -1 to the squared is positive. So what if I put n plus 1 here? When I plug 1 into that, I would get 1 to the 2nd power, which would be +1. That would be good. Now if I plug 2 in there, I get 2 plus 1, which is 3, and -1 cubed is -1. So this will generate my alternating series. So whenever you need to generate an alternating series, you probably just have to put a -1 to n, or -1 to the n plus 1, or -1 to the n minus 1, however you want to make it match up with the signs. Now I have to divide this guy by n. So I think sometimes in your book, they like you to write it like this: -1 to the n plus 1 or minus 1 times 1 over n. They kind of like to have the alternating portion over off on the side. So we found a way to write, this is not so bad, right? So let's take a minute to talk about summation notation. So write all this down real quick. Using summation notation, we often like to add the terms of a sequence, a sub n. So what we're going to do is we're going to take all those terms that we've been writing out, and we're going to say a sub 1 plus a sub 2 plus a sub 3 plus a sub 4, all the way up to a sub n. And we would like a cleaner, nicer notation. So what we're going to use is something called sigma notation. Okay, so this is sigma notation, or summation notation, or if it was to infinity, we'd call it a series. So this is a very important part of Calculus 2. You're going to see this all the time. This comes up in Calculus 1 as well, but this is a huge part of Calculus 2, using sigma notation. And in Calculus 2, we focus a lot on series. So we have a sub k, which is our sequence, from 1 to n. So by doing that, you are saying that you are going to add up all the terms of the sequence. This notation right here, this symbol right here means to sum or to add up. Okay, that's what sigma's the letter S. Okay, so it means to add. So what we're going to do is whenever you see this notation just simply means add. All you have to do is add up whatever they tell you. This oftentimes is referred to as the index, right? And it tells you where to start. So this is your starting point. This is the value you start plugging in, and this is the value you end or you stop plugging in, okay? So if I gave you 1 over k and I wanted you to write out the terms, and this goes to n, you would write 1 over 1, well, I guess that would just be 1, right? 1 plus 1 over 2, because now I'm plugging in 2, plus 1 over 3, plus 1 over 4, and then how far am I going to go? When am I going to stop? Well, I'm going to stop at 1 over n, because this tells me to stop there, this tells me to start there. Remember, this is k equals 1, oops. This is k equals 2, this is k equals 3, so on and so on and so on, okay? All the way down to k equals n. Now, hopefully you guys have heard of a factorial before. All a factorial means is a number times itself. So we're not going to go too crazy on this, but if I wanted to write this out, I'm sorry, not a number times itself. So if I said 7 factorial, that just means 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, if I said 8 factorial divided by 6 factorial, that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 6 times 5 times 4 times 3 times 2 times 1. So what you do in these cases is you can cancel and you're left with 56. So 8 factorial divided by 6 factorial is just 56. That's all a factorial means, is it means to start multiplying by all the factors of the number down to 1, okay? So we're going to just write out 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial plus all the way down to n factorial. And that's just showing that we know how to use summation notation and we know how to write things out, okay? So now we'd like to take a sum and simplify it and write it with the summation notation, okay? So take a minute to write this down: 1 plus 1/2 plus 1/4 plus 1/8 plus ... oops, plus 1 over 2 to the n minus 1. So they're telling you where to stop. They're actually telling you to stop at this value, 2 to the n, stop at n minus 1. So, and again, remember, this is just an intro section. You're going to spend more time on this in calculus. So what we're going to do is we're going to say, well, this should be the sum of 1 over 2 to the k. okay? And it's going to start at k equals, ooh, this has to be k minus 1. And this has to start at k equals 1, and this has to stop at n, okay? Now, how do I know it works? So what you guys can do is you can take and plug 1 into what you said is the summation. So if we plug 1 in there, 2 to the k, which would be 2 to the 1 minus 1 would be 0. 2 to the 0 is 1. We get 1. Now we plug in 2. 1 over 2 to the 2 minus 1 would be 1/2. 1 over 2 to the 3 minus 1 would be 1/4. And then 1 over 2 to the, and then how do we get this one? We plug n in, that would be n minus 1. So there you go. We can safely say that this is the summation notation for this, okay? Now this one should be easy as well. This starts at k equals 1, but it ends at 9. So it's just saying k squared, right? Because if I plug 1 in there, I get 1 squared. If I plug 2 in there, I get 2 squared. And then I go all the way up to 9. So not everything stops at n. Some things stop at n. Some things stop at 7. Some things stop at or approach infinity. So when you're writing these, you just kind of got to look at your directions. So remember, this tells you where to stop, the value to start plugging in, and this tells you the value to stop plugging in, okay? All right, so now we have properties of sequences. So again, pause the video, take a minute to write all of these down. Okay, so now that you've written these down, here's the thing, is this is a constant C, and what they're saying is that since the summation is just the addition, you're going to say C times A sub 1, C times A sub 2, C times A sub n, so on and so on. Well, that means technically then, couldn't you factor out the C from the whole sum? And you could just move it to the front. So what they're saying is if you're ever multiplying by a constant, you can pull it out of the summation. So like if it was 7 times x squared or 7 times k squared, you could pull the 7 out, work with the k squared, and then multiply the whole thing by 7. So that's all they're saying. For this next one, it's saying that if you have addition or subtraction of two sequences inside of the summation, you can split it. Now this is only legal because it is a finite sum. If it was an infinite sum, we'd have to be more careful. But because it's finite and it ends at n, meaning there is an ending. If it was approaching infinity, that's when we have problems. You got to have special rules for that. But because this ends at n, wherever that may be, that means that this is a finite sum, okay? So this is legal to split it as two separate entities, okay? Two separate summations. So this next one says that if you want to start k at j plus 1, you can do that, but all you do is you go from 1 to n and then subtract off 1 to j, and whatever the leftovers will be the term after j added up. So if I want to go from 1 to 50, I want to add up from 30 to 50, all I do is I say, well, maybe 30 to 50 is too big. Let's say I want to add up the terms from 6 to 10. So all I do is I do the entire series from 1 to 10, and then I subtract off 1 to 5. And the leftovers would be j, or which would be 6 to 10. So it's a way that we can still find a sum without always having to start at the beginning. Okay? So these formulas come up also right here in calculus 1, actually. Yeah, in calculus 1, I believe, yes. So when I teach calculus 1, I use these a little bit in class. They use I's in the book I'm from, but or the book that I work with, but it's fine. So the thing is what they're saying is if you have the sum of a constant, so let's say that I just had the sum of k equals 1 to 5 of 6. Well, what they're saying this would be is it would just be 6 plus 6 plus 6 plus 6 plus 6 5 times, right? Well, wouldn't that just be 30? So they're saying, why not just do the n times the c. So whatever the constant was, in our case 6, so we could just do 6 times, and then whatever the stopping point was 5, so we would get 30. So they're just saying that if you ever are just doing a summation of a constant, you can just multiply where you end at times the constant, okay? Now these are a little bit more tricky. I'll write like one out just in case. So what if I wanted to do the sum of k from k equals 1 to 4, okay? So what we're gonna do is this would be 1 plus 2 plus 3 plus 4, right? Easy enough. So this would be what, 5, this would be 10. But what I want to show you is that this formula could have done the same thing. So imagine instead of going from 1 to 4, what if I went to 1 to 758,000? You're not going to have to add all those up. That's too much. So the formula says that you can do the same thing, but all you have to do is you have to tell them the stopping point. In this case, the stopping point is 4. So I would do 4 times 4 plus 1 divided by 2. So this would be what? 4 plus 1 is 5 times 4 is 20 over 2, which is 10, the same number. So this is just you trusting that these formulas work, okay? So that means that like now, what if I wanted to tell you, hey, find the sum from k equals 1 to, I don't know, 25. Well, I don't want to have to write out for k squared. I don't want to have to write out 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared all the way up 25 squared. So what the formula says is just put whatever your stopping point is, 25, times 25 plus 1, which would be 26, times 25 times 2 plus 1, which would be 51, and divide it by 6. So I'm going to take out my calculator, and I'm just going to do 25 times 26 times 51 divided by 6. And I get 5,525, okay? So that's saying that if you took the first 5 perfect squares and you added them all up, you would get 5,525. And you could do the same thing for this one. What if you wanted to add up, the summation from k equals 1 to 4, let's just say, of k cubed. Now, I'll show you the slow way. What we could have done is we could have said 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed. And that would be 1 plus 8 plus 27 plus 64. And we get 102, okay? Or we could have used the formula. And the formula says 4 times 5 over 2. Let me see here. We stopped at 4. 4 plus 1 is 5, divided by 2 squared. So this would be 20 over, wait a minute, did I add wrong? I said 1 plus 8 plus 27 plus 64. It's 100, it's not 102. Sorry about that. I don't know where I got the 102 from. Oh, I typed in a 29 instead of a 27. Yeah, I knew something was wrong. So this has to then be squared. So this would be over 2 squared, which would be 10 squared, which is 100. So we get the same value. Again, it's the same thing, if you do it the slow way or if you do it the quick way. So that's what these formulas do. They kind of help us do things a little bit faster, okay? So now, if we know this information, we should be able to find the sum using these formulas. So pause the video and give these 3 a shot. This one is the hardest one right here. Okay, so hopefully you guys are unpaused from the video. Let me actually write this one better. Hold on. So let me put this one. This one, let me write it over here so I have more room. Okay, so this, I should use my property that says I can pull the 3 out and then do summation. You know what, I'll do it in red. I should pull the 3 out and do the summation from k equals 1 to 5 of k. And if I go up here, it says that that's n times n plus 1 over 2. So this would be 3 times 5 times 6 over 2. Let's see. 5 times 6 over 2. Yep, sounds good. So then this would be what? This would cancel with this, and this would be 15. That would be 45, I believe. So we get 45 for that one. Hopefully we got the same value. We could have done it the slow way. We could have said 3 plus 6 plus 9 plus 12 plus 15. And if we add those up, that's 30, that's 45 as well. So that would have also worked. But again, you want to learn how to use the formulas because sometimes the problems are going to get out of hand. Okay. So now for this one, we're going to rewrite this guy as two separate ones because it said we could. K equals 1 to 10 of k cubed plus the summation of k equals 1 to 10 of 1. So we know that this one will become the formula n times n plus 1 over 2 quantity squared. In this case, n is 10, so we're going to do 10 times 11 over 2 squared plus 10, because this formula says if you have a constant, you just multiply c times n. And in this case, c is 1 and n is 10. So now we just clean this up a little. That will be 55 squared plus 10. And I get 3,035. And again, if I ask you these questions on the exam, just show me this little bit of work. You don't have to go crazy, but you do have to show me something because technically your calculator has a sequence feature and you can just hit enter and not know how to do any of this. So I want to make sure that you show me this little bit of work that shows me you know how to use properties. This one's a little bit tougher because they want to know from 6 to 20. So what I need to do is I need to write this series k equals 1 to 20 of 4k squared minus, now what I want to subtract off all the terms right before the 6. So I'm going to do k equals 1 to 5 of 4k squared. So I hope you guys see that what I'm doing is all of these terms are the first 5 terms and I'm subtracting it off from that. So that will leave me with only the 6th term and up to 20, okay? So this will be 4 times, now k squared. Let's see, k squared, oops. K squared was n times n plus 1 times 2n plus 2. So this would be n, which would be 20, times 21. And then it said times 2n plus 1. So that would be 40 plus 1. All over, I believe it was 6, right? Yeah, 6. Okay, and then minus, now this would be 4 times, it's going to be over 6 again, right? But this time it's going to be 5 times 6 times 2 times 5, which would be 10, plus 1, which would be 11. Okay, so let's see what we get this time. So I'm going to do 20 times 21 times 41 times 4. And I'm going to divide that by 6. So that should be 11,480 minus 30 times 44 divided by 6, 220. So I'm going to do 1,480 minus 220, and I get 11,260. And that would be my sum. So that is the sum of this. So the sum of, k equals 6 to 20 of 4k squared is worth this. And that's because, remember, think about it. I'm writing out the first 20 terms of this series, and then I'm going to wipe out the first 5. So that'll leave 6 and up. So that's what this notation is, this last little notation is for, is to help you deal with those situations. This one right here, this guy right here. That's what this one's for, if they ever ask you to start somewhere else, okay? So hopefully that helps you guys get started on sequences. There's kind of a lot of information in this section, but I think that's a good starting point. The next 2 sections are actually a little bit easier. Arithmetic and geometric sequences are pretty easy to work with because they have like very specific patterns. But that's going to do it for this video, guys. Thanks for watching.